So until now, we have looked at entropy and how to estimate entropy when we know the end states, and how also the irreversibilities manifest themselves as entropy generation, and the relationship between the change in entropy, the entropy generation, and the entropy transferred to a system. And we have seen how this manifests itself, and we have seen some examples how to calculate entropy change, how to calculate the entropy generated, and so on. Now that we have completed our study of the first law and the second law, the first law talking about internal energy, entropy, internal energy, enthalpy, and changes in kinetic and potential energies, and the second law talking about what is possible and what is not possible, and also talking about entropy as a state function or a property of the system. We are now ready to take the next leap and look at few examples of how these first law and second law are used in everyday devices, in engineering devices. Perhaps the most important of these engineering devices is power production, that is, the production of mechanical power, or more importantly electrical power, using chemical energy stored in various fuels. So for example, coal power plants convert chemical energy in coal to electrical energy, and for example, gas turbines convert the chemical energy in natural gas or the chemical energy in kerosene to kinetic energy of gases that can then be used to propel an airplane, or to electrical power when they are used in stationary power applications, and so on. So today in this video, we will be taking an overview of what is called the Rankine cycle, one that is used in coal power plants across the world, and that has been used for many decades now to produce electricity from a very abundantly available natural resource, which is coal, and we'll take a look at how this works, right? So this comes under the broad umbrella of power cycles, and one of the type of power cycles is to use a vapor. As I said, we will also look at gas turbines, which do not use vapors but which use gases instead. So one of the ways of doing power cycles is through vapor cycles, and one of the vapor cycle is the Rankine cycle. So we will take a look at the process that is used in a Rankine cycle in a short while. But before we do that, we need to revisit some of the principles that we learned so far in this course. What are those principles? Those principles state that, for example, if I have to compress a fluid, right, from a particular pressure to another given pressure, I would rather do it when it is a liquid than a vapor, because that would consume a lot less work than it would if I were to compress vapor instead. And if I were to expand, then I would rather expand a vapor because that gives me a lot more work than the expansion of a liquid would give me. So these are the two principles that are used. Another principle that is used is irreversibilities cause degradation in performance, and that real irreversible processes result in lower work output and higher heat consumption or thermal energy consumption, or basically higher fuel consumption as compared to reversible devices. So we would try to have as many processes as possible without irreversibilities, and one of the processes that is nearly irreversible is when you have a phase change process, because when the phase change process is taking place, there is no change in temperature, and so therefore the temperature across different points inside a system remains constant. And so that's one process that we are going to exploit in this Rankine cycle here. So we want to underline this again. So reversible work output from a steady flow steady flow device with changes in kinetic energy and changes in potential energy neglected we saw was equal to m dot times integral in to out V dP, right? This implies that pumping and compressing we would prefer to do in liquid state, and expanding so that we get work output we would rather do it in vapor or gas state so that we get the maximum work output. Why? Because we want to keep V very small or as large as possible depending on what we are doing. If it's a work consuming device, we would like to keep V as small as possible. If it's a work producing device, we want to keep V as large as possible, which is why we would rather do the pumping and compressing in liquid state, and expanding to get work output in a turbine, we would rather do that in a gas phase, right? And then we would like to do heat addition isothermally during a phase change process. Of course, we cannot carry out the entire heat transfer to the system isothermally. There will be some temperature change, but if we can minimize the changes in temperature, then we would minimize the internal irreversibilities within the system and therefore achieve higher efficiencies. And so that's what is done in a Rankine cycle. So let's jump and take a look at how the Rankine cycle looks like on a TS diagram, that is on a temperature entropy diagram. So I'm going to draw the temperature entropy diagram of water. This is the temperature entropy diagram of water. Although we use coal and we want to convert the chemical energy of coal to electric power, the working fluid inside this Rankine cycle is water or steam, and so therefore we look at the TS diagram of water and not the TS diagram of coal. Coal is just burnt in air, and its exothermic heat of reaction is used to provide heat to the working fluid, which is water. And so therefore we are looking at the TS diagram for water and not that for coal, right, which is a solid anyway. So this is how it looks like, and this is the dome that we are all quite familiar by now, right? And we start with a subcooled liquid, and let's call that state 1. So state 1 is a subcooled liquid perhaps at nearly room temperature. And pressure nearly is a little bit less than atmospheric pressure. So perhaps we start at 35 degrees Celsius and perhaps about 400 kilopascal. So 40 kilopascal. So if we start below atmospheric pressure, and then we use a pump to pump this liquid, and remember when we pump, we would like to pump it as a liquid, and that will get us to state 2, right, which is also a subcooled liquid. And approximately the same temperature, because the temperature does not change appreciably, but we go to very high pressures. We go to as high as 15 megapascal to 20 megapascal. In some power plants, we do go to higher pressures, but this is what we are describing here is what is called a subcritical thermal power plant, in which we do not go above critical pressures. As you know, the critical pressure of water is about 22 megapascal. So we do not go to those pressures or higher than those, but we stay under those pressures, and so therefore we have lower pressures in a subcritical thermal power plant. And then we use, of course, a pump to achieve this increase in pressure. So there's a pump here, right? And then we provide heat to this fluid, and therefore we raise its temperature and move along an isobar from 2. So 2 is at a higher pressure, but we move along an isobar and reach saturated liquid state, and this is heat addition. So let me also write the process here. So 1 to 2 and 2 to 3 heat addition accompanied by sensible heating. That is, the temperature of this fluid goes from T2 to T3 here, assuming this is state 3, right? And this, where does this energy come from to heat up the water from T2 to T3? It comes from the exothermic reaction of coal, and the gases and the water are exchanging heat through a heat exchanger. That is, they are not in direct contact because the coal gases and the steam cannot be allowed to mix, but they exchange heat through a heat exchanger. In other situations, this could also be heated from steam that is taken from different parts of the system itself, but that's a complication that we will come to later. We just have to understand that the energy required for raising the temperature from T2 to T3 comes directly or indirectly from the heat of combustion of coal, that is the fuel that is used, right? And at state 3, we have a saturated liquid. So the saturated liquid is at a state which is approximately 350 degrees Celsius and between 50 and 20 megapascal. Of course, depending on the pressure to which it is pumped, it would reach a saturation temperature that is different. That would be the saturation temperature corresponding to the pressure at which it exists in the saturated state at 3. Further, we have further heat addition that takes the saturated liquid to a saturated vapor state at the same pressure, and so we have a saturated vapor here at 4. So at 4 we have saturated vapor, and this also the temperature and pressure do not change appreciably from 3 to 4 because it's a constant pressure. In other words, it goes along an isobar, and as you know, there's a phase change process taking place. There is no change in temperature as long as the pressure is held constant. And so 3 to 4 is heat addition this is latent heat of vaporization. Because we want the vapor, because we want the fluid in its vapor form to be able to expand, we would want to convert it from liquid to vapor. That is one reason. The other reason is that heat addition can take place at constant temperature, which means that we minimize the reversibilities associated with heat transfer, where necessarily otherwise if we don't have change of phase, we would have a temperature gradient within the fluid, and that would cause irreversibilities, whereas a phase change process would carry out the heat transfer with minimum irreversibilities, and so that's an added advantage of converting the liquid to a vapor, right? And then we can from 4, this is further heated until we get to a superheated state. Let's call that 5, and 5 is a superheated vapor. This is approximately 550 degrees Celsius and 15 to 20 megapascal pressure. So it's heated to a higher pressure temperature, maybe not this high, maybe we can go. So at 5, it's a superheated vapor, and again from 4 to 5, the process is a heat addition and this is again sensible heating. And at 5, the temperature of the fluid is about 550 degrees Celsius. That 550 comes from a material's limit, and beyond this temperature, the turbine blades start to soften, and there is a danger of them breaking. And so therefore, typically, this is the maximum temperature that subcritical power plants go to. Of course, the metallurgy of these turbine blades has improved, and there are also many thermal barrier coatings and other active and passive ways of managing temperature that have been developed. And so more recently, these are able to go to a much higher temperature. But by default, we will assume that this will go up to 550 degrees Celsius or so. And then this vapor is then expanded in a turbine. Six, right. And this expansion process results in work done because this vapor expands in a turbine. The turbine is rotating a generator, and this generator generates the electricity that we all consume in our houses, in our offices, and in other industries and so on. And we end up at a state 6, which is at or just inside the vapor dome. In other words, it's either a saturated vapor or it is a high quality saturated liquid vapor mixture. In other words, it's a saturated vapor with vapor fraction 1, or it is a liquid vapor mixture with a quality of 90% or greater, and that's how that is what 6 is. So I will write 6 again as I'll write it here. That 6 is either a saturated vapor or a saturated vapor liquid mixture with a high quality of 90% or so, and this temperature is around the temperature is about 35 to 40 degrees Celsius, and the pressure is about 40 kilopascal. And then this is cooled down. We lose heat in a condenser and get back to state 1. But before that, we need to write here 5 to 6 is a expansion work in a turbine. If we have an isentropic turbine, 75? 75 degrees, okay. So this is around 75, okay, 75, 80 degrees Celsius. And if this is an isentropic turbine, this line would be perfectly vertical. But in real turbines, as we have seen with isentropic efficiencies of 85 or 90 or 75%, we could expect that this would curve to the right, and end up at an isobar which is passing through 6, and then we cool down to 1. So, this is the process. So, 6 to 1 is a heat rejection step, and some of this heat rejection happens in single phase, which means it's a sensible cooling, and some of it, a large portion of it in fact, happens when there is a liquid vapor mixture. In other words, it's a latent heat of vaporization, or you can say latent heat of condensation, that is then rejected to the outside, most likely to the atmosphere, sometimes to rivers and to oceans. This heat is rejected, and so the fluid comes back to state 1, and this is not as if a mass of fluid is taken from 1 to 2, 3, 4, 5, 6 and back to 1. It's a continuous process in the sense that there's always fluid at state 1, there's always fluid at state 2, 3, 4, 5, 6 and so on, and there's fluid everywhere in between, which means that fluid is always continuously circulating. And although if we follow a parcel of fluid, we go from state 1 to 2 to 3 and so on up to back to 1, but at any given time there's fluid everywhere in the system, and so there's at any given time there's always a piece of fluid that is at state 1, there's always a piece of fluid that is at state 4, and there are always parcels of fluid that are everywhere between 1, 2, 3, 4, 5, 6 and 1. So, this is how the cycle operates, and it operates continuously. We can now see how this cycle looks like on a block diagram. In other words, how does it look like from a components of the system kind of perspective rather than from a cycle perspective. So, let us look at that also. So, we start from state 1, which is a subcooled liquid, and as I pointed out, we go through something called a boiler feed pump, which takes it to state 2, which is a high pressure, low temperature liquid, and from here we do a sensible heat addition. This is sensible heat addition. That takes us to a saturated liquid state 3, and then from there we do a latent heat and then that brings us to state 4, which is a saturated vapor, and then we have the third stage of heating, which is again it's a heat addition. This is sensible again, and from 5 we go to a turbine and end up at say state 6, and then this turbine of course does work on a generator typically, and this generator generates the electricity that we use, and this here goes through a heat rejection step in a condenser. And ends up back at state 1, and the cycle repeats all over again. So, this is a subcooled liquid. This is also a subcooled liquid, albeit at a higher pressure. And this is a saturated liquid, and this is a saturated vapor, and here this one here is a superheated vapor, and here we have a saturated vapor or a high quality liquid vapor mixture. So this is how it looks like from a device perspective. That's how it looks like from a cycle perspective. So this is how a Rankine cycle operates, and most of the electric power that we derive today is from this cycle. And of course, there are many advantages as well as disadvantages of this cycle. One, we use fuel that is considered to be very dirty because it creates a lot of pollution, not just in terms of carbon dioxide, but also in terms of particulate matter, in terms of sulfur and phosphorus and mercury emissions, all of which are very harmful to the atmosphere, to the water bodies, as also to the soil around us. And of course, it releases a lot of greenhouse gases, and that contributes to global warming, as we know. But however, these still continue to be the workhorses of our electricity generation ecosystem, and we get a majority of our electric power using the Rankine cycle. And so it's something that we need to know, but we also need to recognize that this cycle has been responsible for climate change, for global warming, and that we need to come up with either improvements to this cycle, make it better, make it more efficient, or figure out a way to do this cycle without the harmful emissions or without the greenhouse gas emissions that it entails. So in the next video, we will look at some of the calculations on how to estimate efficiencies, how to estimate the heat input required, how to estimate the work output of a Rankine cycle operating between certain temperature and pressure conditions. So that's what we will do in the next video.